this week we're going to be looking at the next topic in higher physics, which is the photoelectric effect. So you see how we looked at interference a month ago or something like that. Interference is where we see sound and light waves. Well, sound and light, should I say, act like waves. Okay, we see that the crests interfere with each other, the troughs waves interfere with each other and either constructively interfere or destructively interfere, etc. The photoelectric effect is an experiment we can do that actually proves that light can also act like a particle. Okay, so interference is where light acts like a wave. The photoelectric effect is where light acts as a particle, and this is kind of an introduction to quantum physics or quantum mechanics. Okay, where things just start to get a little bit weird. Okay, but yeah, it can act like a wave or a particle. So let's get started. There we go. Why that took so long? Okay, so things first, I want to talk about the structure of an atom for a second. Okay, I want you to start thinking of a structure like this. So we've got obviously our nucleus in the center. Our nucleus has our protons and our neutrons in it, and then we have our electrons around the outside. Now, you've probably had this when thinking of what an atom looks like. You to throw this in the bin, okay? Because, well, it's not a particularly accurate way of thinking about it, the way that these electrons are drawn in, okay? I want you to now start thinking of an atomic structure like this with these nice circular orbits going round the nucleus. And these circular orbits represent the orbits of electrons. Okay, so let's read through this. So electrons in atoms are only permitted to have certain energy levels. Okay, so electrons have certain energy associated with them, but they can only have certain energies. Okay, so they can only have 1 joule associated with them, then 4 joules, then 7 joules, like that. No electron could have 3 joules. Okay, only 1, 4, 7. Now, obviously, I'm saying 1 joule, 4 joules, 7 joules. That's quite a lot of energy. Okay, electrons actually have very, 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 very small energies associated with them. In the region of 10 to the negative 18 joules, but I'm 1/4 just because it's easier. Okay. So electrons have limited energy levels. Therefore, about the nucleus at certain heights. So, for example, this orbit here would have the lowest energy associated with it, and the second it would have the second lowest energy associated with it, and then the outside orbit with the highest energy associated with it. Okay. Now, electrons can gain energy and jump up to higher orbit. Okay? And we'll talk about how they can gain energy in a second. So they can gain energy if they gain exactly the correct amount of energy. They can jump. And if they gain enough energy, they can actually jump all the way up and escape the atom entirely. Okay, and this is called ionization. So we came with ionization in national. If you've done chemistry, you'll have done a lot more work on ionization. Ionization is when an atom gains or loses an electron. So in this case, obviously, we're losing an electron. It's enough energy to just leave the atom. And therefore, when we have an ion, okay, an atom has an equal number of protons and electrons. The protons and the electrons, the charges cancel each other out, so the atom is neutral. If if an electron leaves the atom, then will obviously be more protons than there are electrons, therefore there'll be an overall charge. We call it an ion. Okay. Now, how can an electron actually gain energy? Well, one way that an electron can gain energy is by absorbing the energy from a photon. A photon is a particle of light. Discuss the light's a wave, but at the start here, photons you can actually think of as part of light, okay, or you can think of light as a particle as well, and we call a particle of light a photon. Okay, so how does that work? Well, we can look at this picture and this. Okay, a photon can fly. Okay, this is the genetic symbol for a photon. Okay, we arrow, squiggly arrow. Okay, so comes in. Okay, and the electron absorbs energy. Okay, if it's a correct amount of energy, it will jump up to the excited state. Okay, that's what we kind of call it when it jumps up to a higher state. We call it an excited state. Okay, it has more energy. So it'll have, say, 1 joule of energy here. This one comes in with 3 joules of energy. So it absorbs the 3 joules, then it's up to the 4 joule state, let's say. So that's what happens. Okay, this is, you can just like a little cross of the image that we're looking at earlier. So like our nucleus would be in here, and these are just energy levels in the atom. Now this is just kind of a more general statement that I spoke about at the start. Light can be observed as a wave or a particle depending on how we observe it, and this is called wave-particle duality. Now I don't need you to worry too much about that. That's more advanced higher, but you do need to be aware that light can be observed if we look at interference experiment. It looks like a wave, and if we look at it in this sort of context, it looks like a particle. Okay, it can look like a particle, it can look like a wave, depending on how we observe it, depending on how experiment we do. Okay. So we've discussed photons, we've discussed that electrons have certain energies associated with them, we've also discussed that electrons can absorb energy from a photon. Okay, we're just going to be discussing the energy of a photon in more detail. Okay, so if a photon is to release an electron from an atom, or if a photon is to just be absorbed by an electron to move up an energy level, it needs to have energy, to have enough energy. And the energy of a photon is given by this formula. Okay, it's quite a nice, easy formula because E just stands for energy, as you would expect. F just stands for frequency, as you would expect. But this H is actually a constant, and it's called Planck's constant. Now, I keep meaning to cheat this. In your day sheets, it's just 6.63. Okay, so if you're writing this down, don't write out 6.62, just 6.63 times 10 to the negative 30, please. Okay, so, when I was at university, I used this number that kind of stuck in my head. Okay, so you just use it to 3 significant figures as you would expect. Okay, so 6.63. You do not need to remember this as given in your data sheet, okay, as well as. So yeah, this is a constant, which makes this equation really quite nice because if you know the energy of a photon, you automatically know the frequency of a photon. If you know the frequency of a photon, you automatically know the energy of a photon. And they have a nice relationship. You know, if the energy of a photon goes up, the frequency of a photon goes up. If the frequency of a photon goes down, the energy of a photon goes down. Okay, so nice and simple. So just a wee worked example. So if a photon has a frequency of 8 times 4 5 times 10 to, sorry, 0.45 times 10 to the 14 hertz. What is the energy associated with the photon? We know the frequency, we ultimately know the energy because all we need is constant. Unfortunately, I have used 0.6. So I changed this. Apparently, but you get the idea. All you need to multiply the frequency by Planck's constant, and you get the energy. Now, just a general thing to look out for when you're doing these problems. Generally, energy associated with photons or electrons in that case is really, really small. Okay, I said you're usually looking at around the times 10 to the -19 region. It doesn't need to be times 10 to the -19, but that's the sort of region you're looking at. And the frequency of a photon, you're usually looking at something along the times 10 to 14. So frequency should be really big and energy should be really small. Okay, so if you get it the other way around, you've probably done something wrong. Okay, so experiment that we do to kind of prove that photons are particles, okay, and light is a particle, is something called the photoelectric effect gold leaf experiment. Now, at this point, we do this experiment. Obviously, we can't do that, and so I'll try my best to explain it to you, show photos as well. Okay, so what we do is we have this sort of weird contract here, and just like a metal box, and this little strip here is just metal, and we have a little gold leaf. Okay, so it's like a little strip of gold. Usually it just hangs down like that, but we can charge this whole thing up just using like plastic rods. We can charge this whole thing up either positively or negative. So when it's positively charged, this whole thing, okay, what that means is you've removed electrons. Okay, if you remove electrons from something, then it becomes positive charge. If you introduce electrons in the system, it becomes negatively charged. Okay, and regardless whether it becomes positively charged or negatively charged, this gold leaf, because it's really light, gold leaf will repel from this metal plate, and it'll just sort of like stand up like this, okay, because like charges repel each other. Okay, so if everything is positively charged, this gold leaf will just sort of repel, it'll just like hang like this, or if all negatively charged, then the gold leaf will also repel and just kind of lie like this. Okay, so this gold leaf is repelled like this. Now, if we positively charged this, I realised I could look at a larger image of this. That would probably be better. If this whole system was positively charged, let's say, and we shone red laser light onto this, nothing would happen. Okay, it would have no effect. Okay, and if we negatively charged the system, it would still have no effect. Okay, nothing would happen. Nothing would happen. Now go to the next picture. Okay, we're now just positively charging this. So remember what positively charging is if we take electron away from the system. And we shone ultraviolet light onto this system. Still nothing would happen. Okay? Then if we took the system and negatively charged it, so that means that there's an excess of electrons and we shine ultraviolet light onto it, then the leaf falls back down. And if the leaf falls back down, that means that these things are no longer repelled by each other, okay? Which means that everything's kind of gone back to neutral. Now let's explain why we see no effect here, but we see that the system is sort of discharged when we shine ultraviolet light when it's negatively charged. Now, we discussed earlier that energy of a photon and the frequency of a photon are linked. Okay, energy is equal to Planck's constant multiplied by the frequency. So if frequency goes up, then the energy goes up. Okay, now ultraviolet light has a higher frequency than visible light. So therefore, ultraviolet light has a higher energy associated with it. Okay, so ultraviolet light has a higher energy associated with it than laser light, which makes sense because when we go out in the sun and stuff, it's always the UV light that can affect our skin. That's why our sun creams and stuff have UVA and UVB like filters, because we don't want them to be damaging our skin, because light of higher energies can be damaging to us. Okay, so if you kind of forget which way around it is, just kind of think of sun cream and stuff. So UV light has a higher energy associated with it. So when we use red light, okay, it doesn't need to be red light, it can be any visible light, but red light for this example, we don't see anything happening. And that's because the photons that are being emitted from this laser don't have enough energy associated with them for the electrons to escape the atom. So if we come back here and look at this, okay, we're remembering that we have our, let's say we have our electrons here in our atom. Our red light is coming in, but our red photons don't have enough energy to allow the electrons to move from here out of the atom. Okay, so the red photons come in, and yeah, the electrons might jump up a couple of levels, but the electrons remain in the atom, and nothing overall happens. Now, if we go back here and we look at this one here where it has positively charged. Now, this whole thing that we've been talking about is getting electrons to leave the atom. Now, if it's positively charged, that means that there's actually less electrons overall anyway. So there's actually no electrons to get rid of. Okay, what we need for this whole experiment to work is an excess of electrons that we want to get rid of. Okay, when it's positively charged, there is no excess of electrons to get rid of. Okay, so again, nothing happens when we shine ultraviolet light onto positively charged system. But when we shine ultraviolet light on a negatively charged system, we do see something happening. Because when it's negatively charged, we have an excess of electrons here. We have, you can think of it as like a wee sea of electrons on this plate, let's say. Okay, so this sea of electrons, when ultraviolet light comes in, the ultraviolet light has quite a lot of energy associated with it. So these photons come in, and these photons will be absorbed by the excess electrons, and those excess electrons will gain enough energy to escape, to escape this bit of metal. Okay, the atoms in the metal. Okay, they will gain enough energy to leave the atom, the metal atoms entirely. Okay, so they'll just sort of fly off, you can think of it, and just go away. Okay, so the ultraviolet light has more energy associated with it because it has a higher frequency. The photons of the higher energy come in, the photons are absorbed by the electrons, and because they have enough energy, okay, they have high enough frequency, the electrons therefore gain enough energy to escape the atom entirely. And when they escape, this system is no longer charged, okay, because the excess electrons have left. And if the excess electrons have left, then you're left with an equal amount of electrons and protons again. So it's just neutral, therefore the leaf falls down. Okay, hopefully that has made sense. It's not ideal when we can't actually do the problem. But just remember, this only works when it's negatively charged, okay? And it only works when your light source has a high enough frequency, okay? So this slide is just kind of going over what I've just said. This is quite a nice video if you want to watch it. I'm not going to put it on because I don't think when I put on videos the sound works when I'm recording, but you feel free to watch that. So just to summarize, the gold leaf only discharges when the gold leaf is negatively charged, okay? And it only discharges when the frequency of the light is sufficiently high. Okay, this is because the photons with high enough energy are releasing the electrons from the gold leaf. Okay, so the photons are coming in, the electrons are absorbing the energy, and they have enough energy to leave the atom entirely. Just a little side note, okay, using light of a higher irradiance, so remember irradiance is just a fancy word for brightness, okay, so using a brighter light will release more electrons, okay, only if the light is above a certain frequency, okay, so only if it's like ultraviolet light, but if you use a brighter light, it will release more electrons because a brighter light or a light of a higher irradiance just means that more photons are being released from that light. So if there's more photons being released, then there are more electrons that can absorb the photons. Okay. Now, this experiment can sometimes be actually, I'll go over a question like what I'm about to explain. I don't think it'll come across if I'm just trying to explain it without a question. So I will go over a past paper question about the photoelectric effect. Okay, so why does this prove that light is a particle then? Well, if we consider light as a wave, then what a wave is a transfer of energy. Yeah, just like a constant transfer of energy. That's what a wave is. So if light was a wave, then we would expect energy to be transferring to the electrons gradually. Would expect the electrons just to be constantly gaining energy if we were shining a light on the atoms. The electrons would just be gaining energy gradually, and then if we just waited long enough, the electrons would gain enough energy and jump out and escape the atom. That doesn't happen, okay? We can shine a red laser light on that experiment for as long as we want to, and nothing will happen, okay? Nothing will happen. Therefore, we can say that, well, in this case, light isn't acting as a wave because if it was, we could just shine a light of any energy on it, and if we just waited long enough, the energy would transfer to the electrons eventually, and the electrons would be able to jump up, but that doesn't happen. Okay, so we see that either light releases electrons or it doesn't. Okay, it is nothing to do with just how long we wait. Okay, the light that releases the electrons has a higher energy than the ones that don't. Okay, now we've been talking about how electrons are only released when photons of a certain frequency are there. Okay, now this certain frequency that we've been talking about is called the threshold frequency. okay, which is just FO, okay. And the threshold frequency, it just means more or less photons that have the threshold frequency or above the threshold frequency, those photons will release the electrons. Okay, easy peasy. And this is what we would expect to see just as a wee graph. Okay, so doesn't matter how bright this light is, okay, that's being shown here. If it doesn't have at least the threshold frequency, then no electrons are being released. Now it says current here because remember what the definition of current is, or what current is. Current is just a flow of electrons, isn't it? Okay, so if we are releasing electrons into a wire, for example, then those electrons that are being released is just current. Okay, so above the threshold frequency, we see that there are electrons being released. Okay, that's as easy as that. Okay, above a certain frequency, electrons get released and we get a current of electrons. No, no, that's not what I meant to say. Now, so we have this threshold frequency. So above this certain frequency, photons get released. Therefore, we must have a sort of threshold energy that above this certain energy, we get electrons being released. Now, for some reason, calling it threshold energy would be just too easy. So they've called it the work function, which makes great sense. And we call it E0. Okay, now remember work, the word work does just mean, oh, sorry, didn't mean to do that. The word work is just energy. Okay, like work done is just an energy. Okay, so the minimum energy required to release an electron from a surface is called the work function, and it just has this relationship. So more or less exactly the same as E is equal to HF, but it's the work function is equal to H times the threshold frequency. So more or less, this is the minimum energy that a photon can have to release an electron from its atom, and this is the minimum frequency that a photon can have to release an electron from an atom. Okay. Right, so different metals actually have different work functions. Okay, so more or less different types of atom require different energies to allow electrons to be released. Okay, so for example, if we looked down this list, you don't need to remember these, don't worry. But let's say like if we looked at calcium or potassium, let's look at potassium. Okay, we can see the potassium is 2.3. Okay, and we can see that nickel is 5.01. So that means that nickel, you would need photons of a higher energy to release electrons from a nickel atom, and you would need less energy to release electrons from a potassium atom. Okay. Usually we use zinc when we're doing experiments, but you don't really need to know that. It's just kind of extra information. Now, this bit is quite important. So obviously we've been saying that if we have a photon coming in and our electron absorbs that energy and it's released from the atom. Now, if let's say our electron needs 10 joules, it needs 10 joules to escape its atom. And this photon comes in and this photon has exactly 10 joules. Then our electron would absorb that 10 joules and it would escape the atom. But then it wouldn't have any energy to do anything else. The electron would just escape the atom and then just do nothing because it would have no excess energy. It's used all of those 10 joules to escape the atom. But imagine that the electron still needs 10 joules to escape the atom, but our photon this time has 14 joules associated with it. So this 14 joule photon comes in, the electron absorbs all 14 joules, it uses the 10 joules to escape the atom, but then it has this 4 joules left over that it hasn't used. This 4 joules will be used as kinetic energy, okay, and it'll fly off using those 4 joules. Okay, so this is what we are going to be doing now. Okay, so the work function, remember, is just the minimum energy. Would allow the electron to escape the atom, but it would just be stuck there, wouldn't have any excess energy. Okay, so if the energy of the incoming photon, remember you can work it out like this, is greater than the work function, then the extra energy will appear as kinetic energy of the electron. Okay, so this is that, like if I had a electron coming in, a photon coming in 14 joules, and the electron, then those 4 joules would be excess. Oh, don't know what happened there. And it would appear as kinetic energy. Okay, so we can work out the kinetic energy of an electron by these two equations. Now, it looks more complicated than it is. It's the kinetic energy of the electron will be the energy of the photon take away the work function. Remember, the work function is just the energy required for the electron to escape. Okay, so it's more or less 14 joules, because that was the energy of our photon in that wee example. Take away 10 joules, because that was the energy required for our electron to escape, is equal to 4 joules. Okay, so it does look more complicated than it is. Oh, I don't know why the A and the B are just there. Okay, so let's do a worked example. Okay, this is quite a common one to get in an exam. I do realize this has been a long video, sorry about that. Okay, so radiation of frequency 5 times 10 to the 14 hertz can eject electrons from a metal surface. Calculate the energy of each photon of this radiation. So let's just focus on that first, because that's quite easy. Okay, we've got a frequency of a photon, and we're just trying to work out the energy of a photon. So yeah, that's a frequency. We're just trying to work out the energy. Again, I'm so sorry that I've used 6.626. It should just be 6.63. So we just multiply our frequency by our Planck's constant, and we get 3.3 times 10 to the negative 19 joules. So this is our energy of our photons coming in. Okay. Then it says photoelectrons. Now, when it says photoelectrons, it's just meaning electrons that are being ejected because they have a what's the word? Absorbed. Sorry, absorbed a photon. Okay, so photoelectrons are just electrons that absorbed energy from a photon. So photoelectrons are ejected from a metal surface with a kinetic energy of 7 times 10 to the negative 20 joules. Calculate the work function of this metal. So more or less it's saying that the leftover energy that it has is 7 times 10 to the negative 20 joules. Okay, so calculate the work function. So this is our list of things we know. We know that the energy of the photon is 3.3 times 10 to the negative 19, and we know that the leftover energy is 7 times 10 to the negative 20 joules. And we're trying to work out the work function. Okay, so this is our equation, or obviously we can just have EK is equal to E take away E0. Okay, this is just, you can just write it like this because E is equal to HF and E0 is equal to HF0. Okay, so we know that the kinetic energy is 7 times 10 to the negative 20. We know that our energy of our photon is 3.3 times 10 to the negative 19, take away unknown. So we can just rearrange it, and we can work out that our work function is 2.6 times 10 to the negative 19. Okay, that's us, I believe. Yeah, so that's us. As I said, it is quite a long video, so I do apologize about that. I will put out another video of me just kind of going over a past paper question as well, just to show you what type of question you would be expected to do in this. I hope that makes sense. It's not the easiest topic to explain over video. So if you do have any more questions or just want me to explain it again, please, please, please just let me know. Okay. And that's us for today.